Hello, this is a part of IEEE 802.11 Tkip video series on securitytube.net. In this video, I'll be talking on message integrity in Tkip WPA protocol. The algorithm is especially known as Michael. In the earlier web standard for message integrity and tampered proofness, a ICV or integrity check vector was added at the end of the payload of the packet. Unfortunately, ICV was a CRC checksum function, so it was very easy to tamper any message, to change any byte in the payload and easily adjust the ICV so that receiver of the packet will not be able to find out whether the message is same as the transmitter's sent message or it has been tampered by some eavesdropper. To address this issue, in Tkip, the message integrity, a little bit stronger message integrity standard was introduced without having much overhead on the hardware portion of the devices. While designing Tkip protocol, one of the constraints was to design a protocol in such a way so that the existing hardware will be able to support the protocol, and with the help of simple firmware upgrade, the Tkip protocol will be able to solve the important problems seen in the web protocol. So MIC, or the message integrity check, is one of them. Michael or MIC function is designed for very low bandwidth CPUs. Generally, upgrading a client is easy, but for APs, hardware upgradation is very cost effective. Now, in the key length for computing MIC is 64 bits. The MIC is computed over source address, destination address, and data part of it. Now, why not only data? If some eavesdropper changes the source address and destination address, it is easy for the eavesdropper to direct that packet to non-intended destinations. So protection against packet modification as well as protection against header forgery can be achieved with MIC protocol. Before going into detail about how exactly Michael or MIC is computed in Tkip, first let's talk about what is MIC. What do you mean by message integrity? For achieving any message integrity for any protocol or for any standard, generally some bits are added at the end of the transmitted stream, and it should be possible for the transmitter as well as receiver who have the secret key to compute the MIC value. So transmitter will be appending every packet with the MIC value. This MIC value is some checksum. It can be checksum, but it is generally a digest of the message, so that any bit change in the original message will change the digest in non-predictable ways. So if any eavesdropper changes any message while the actual message was in transit, he will not be easily able to change the MIC, and the receiver of the packet will be able to know that the original message is being tampered, and he will not accept that message. Now in web, ICV was used as a message integrity, but it's not a real protection because ICV can be easily recomputed. Now, a basic idea behind computing MIC or message integrity code is calculating a checksum over the message bytes so that the modification is very difficult. Now this MIC is combined with secret key so that the only authorized parties can generate and verify the MIC. Generally, only MIC is not the original text message, and MIC is not transmitted. The MIC and the text message as a whole is again encrypted. So the receiver has to first decrypt whole message. He has to separate the MIC part of it. He has to separate the payload part of it. After that, he has to recompute the MIC, check whether everything is fine, and only then the receiver will accept the message. Now, as Tkip is required to work over existing hardware, it cannot use computationally intensive cryptographic methods. Now, even if all this computation is moved to software part of it, still the existing access point cannot perform heavy computations because existing access points are made with low price chips, and they cannot do all these computations in software as well. So thus Tkip uses a method of computation for MIC as a Michael. You cannot choose the ideal or best algorithm, best cryptographically secure algorithm for MIC because it will be computationally intensive. So Michael uses some simple shift and add operations which are not that computationally expensive instead of multiplications and other operations which are computationally expensive to get the MIC value. Now, how exactly Michael or MIC is calculated? It is operated on the MSDU or MAC service data unit rather than MPDU or MAC protocol data unit. Now, MAC protocol data unit or MPDU is actual frame which is transmitted on the air, and MAC service data unit is the unfragmented frame. So MPDU is the fragmented frame and MSDU is unfragmented frame. MIC is always appended in the MSDU so that it can be computationally or all the computations can be performed in device driver rather than on the adapter card. If MIC has been added in every MPDU, then it has to check whether the packet is correct or not in the adapter card itself. Now, as in web, ICV is added per packet, per MPDU. So it is in the adapter card, but MIC is present in MSDU, so it can be done in device drivers. Also, it reduces the overhead as MIC is not calculated for each MPDU. It is computationally less expensive. Now, MIC or Michael is computationally simple. It offers a weak form of security. It is not a very strong form of security, but it's surely considerably better than web. And since the Tkip MIC offers a little bit weak form of security, to counter these drawbacks, it includes some sets of countermeasures which are used. So if the devices finds out that there is some eavesdropper or there is some attacker who is tampering the packets, the countermeasures start kicking in so that the original key will be changed and a new session will be established, and the same session keys will not be used henceforth again. Now, Michael countermeasures are used to reliably detect the attack and shut down the communication to the attacked stations for a period of 1 minute. This is generally done by disabling the current keys and link is shut down for a minute, and after this 1 minute the rekeying is done, and after rekeying the old session keys will not be used again, and so if attacker has to relaunch the attack, he has to take the same effort as he has taken earlier for these new session keys. Again, there is one small caveat here. It can be used by the attacker as a measure of denial of service attack, because once the devices finds out that there is some problem and there is attacker in the media, he will stop for a minute and then he will re-establish the keys. So it is actually a denial of service for the clients. At least theoretically it is possible. How practically it can be exploited, there is recently generated one attack. That's it for this video. Thank you. In next video I'll be talking more about how encryption and decryption is done in Tkip. Thank you.